We've all pictured it, haven't we? A robot helper in our homes, a super smart partner on the factory floor, or a tireless assistant in a hospital. So, why aren't they everywhere yet? I mean, really, what is the holdup? What's really keeping them from being a part of our daily lives?
Well, to understand that, we need to look at where we're trying to go. The big vision right now is something called Industry 5.0, and this is a massive shift in thinking. We're moving on from the old model, Industry 4.0, where robots were basically just there to replace people doing boring, repetitive jobs. The new vision is for robots to amplify what we can do. They're not just tools anymore, they're becoming our partners.
So, here's our game plan for this explainer. First, we'll talk about that dream future with robots. But then we're going to get real and dive into the three huge computational nightmares that are holding us back. We're talking about the gap between a perfect simulation and messy reality, the insane need for split-second decisions, and the challenge of making a robot that isn't just a one-trick pony. And then finally, we'll look at how we're actually starting to solve these supposedly unsolvable problems.
All right, let's start with the exciting part. Section 1, our future with robots. We're moving way beyond simple automation and into a world of true human-robot symbiosis. The end goal here, the absolute dream, is to create what researchers call cognitive partners. Just think about that for a second. A robot that doesn't just run a program, but actually learns from you, from your feedback. A partner that helps you be more creative and more skilled in places that are chaotic and unpredictable, like a busy hospital or a dynamic factory floor. It sounds incredible, right? But to even get close, we first have to solve some of the hardest computational problems you can imagine.
And that brings us smack into our first major nightmare. Section 2, the simulation versus reality gap. This is all about the brutal jump from a perfect, clean virtual world to our messy, chaotic, and totally unpredictable reality. You know, this quote from Eric Zhang just nails it. In a computer simulation, everything is perfect unless you go out of your way to program in some messiness. But in the real world, the universe gives you chaos for free. A robot can work flawlessly for thousands of hours in a simulation, but then in the real world, a slightly slippery floor, a weird shadow from a light, or a box that's just a few millimeters off, and the whole thing can fall apart. So let's break down what this real-world chaos actually looks like to a robot. First up, you've got unmodeled physics. These are all the tiny little things like friction, air resistance, or even a bit of dust that are just impossible to simulate perfectly. Then there's data scarcity. Robots need a ton of real-world data to learn, and getting that is super expensive and takes forever. Put these together and you get brittleness. That's where the robot just fails the second it sees something new. The good news, we're fighting back. We're using techniques like domain randomization, where we intentionally make the simulation super messy and random to basically train the robot to expect the unexpected. Okay, so that's nightmare number 1. Now for the second one, which is all about speed. Section 3, decisions in a millisecond. I like to call this the optimization nightmare.
I want you to imagine the hardest Sudoku puzzle you've ever seen. Now imagine someone tells you to solve it in under 10 milliseconds. Oh, and as soon as you're done, you have to do another one and another, forever. That is basically what we are asking a robot to do every single moment it's operating. These are what computer scientists call NP-hard problems. They are so ridiculously complex that as you add even a few more variables, the time it takes to find the perfect solution just explodes into infinity.
And just look at the scale we're talking about here. That first bar, slam, that's just the robot trying to figure out where it is in a room, and it involves juggling thousands of variables. Then you have NPC, which is about planning its next move. That has to deal with hundreds of constraints all at once. Even something that sounds simple, like just picking up a cup, is this wildly complex optimization problem, and it has to solve all of this basically instantly. And the complexity scales in a terrifying way. Look at this number, 29. That's how many joints or degrees of freedom a really advanced robotic hand can have. Here's the scary part. Each new joint doesn't just add to the problem, it multiplies it. The problem's difficulty grows exponentially. It is a true combinatorial nightmare. You know, all of that insane complexity leads us directly into our third and final nightmare. Section 4, moving beyond a one-trick pony. This is the generalization problem.
So what do we even mean by generalization? In a nutshell, it's the robot's ability to handle something new.
It's not about doing the same exact thing over and over again perfectly. It's about taking what it knows and applying it successfully to a situation it has never, ever seen before.
And why is this so hard? Well, because it's not just one thing. It's having contextual understanding, like knowing a cup isn't just a cylinder, it's something you hold and drink from. It's being able to combine simple skills you already know to solve a brand new problem. It's about handling failure gracefully. What do you do when a door you need to open is stuck? And maybe the hardest one of all is human prediction, trying to guess what a totally unpredictable person is gonna do next. So how are we tackling this? The absolute cutting-edge stuff involves something called Vision Language Action Models, or VLAs. Think of it like this. These models connect what the robot sees with the language we use to describe the world and the physical actions it can perform. This gives the robot a way richer, more flexible understanding of its surroundings, letting it chain skills together to solve new problems on the fly. Okay, we have stared into the abyss of the three nightmares. So for our last section, let's talk about the path forward. How in the world are we starting to solve the unsolvable? What's really wild is that these problems aren't separate issues. They actually stack on top of each other in what you could call a hierarchy of intractivity, basically a ladder of difficulty. At the very bottom, you have just plain geometric problems, figuring out shapes and spaces. That alone is incredibly hard. Then you pile on dynamic problems. You add physics and motion. On top of that, you have learning problems, dealing with all that real-world uncertainty. And at the very top of the ladder, you have cognitive problems, trying to understand what a human wants. Each layer makes the whole thing exponentially harder. But, and this is the hopeful part, computer science is giving us an amazing toolkit to climb that ladder. To tackle that generalization problem, we're using generative AI and those VLAs we talked about. For the insane optimization nightmare, we use clever algorithms called heuristics that find good enough answers but do it blindingly fast. And for the absolutely critical issue of safety, we can use something called formal verification to mathematically prove a robot won't do something dangerous. Slowly but surely, we are chipping away at these unsolvable problems. So if you boil it all down, the grand challenge of robotics is this. It's a constant battle against exponential complexity. But it's not a war on one front, it's a war on three: geometry, physics, and cognition, all at the same time, and all with the unforgiving, hard deadlines of the real world. And that leaves us with one final huge question. As we get better and better at solving these monumental challenges, the question becomes less about technology and more about us. When we can finally build them, what kind of partners will we actually ask our robots to be?